All right, welcome back, everybody. So this is the 13th lecture of the class. This is as close to Friday the 13th we're going to get this month. Midterm's going to come out on Monday. I'll probably release it after class. It'll be due on Wednesday, probably at 5 o'clock. And there will be no office hours on Tuesday or Wednesday. Okay? Okay, so in the last lecture we talked about ODEs with forcing. And so now we're going to go into some really, really powerful stuff related to convolution integrals for general systems. So we're going to start looking at general systems like x dot equals matrix A times x plus some input forcing matrix B times a input vector U. Okay? So before we've been looking at this first part for kind of unforced linear dynamical systems, and now we're going to add this forcing term. But before I do that, I want to just kind of motivate this type of equation with an example from the homework. So writing a system as a linear ODE plus a linear forcing term can be extremely general for linear feedback control. Okay? So the example that we have from class is this theta double dot equals minus sine theta plus some torque tau. Just to draw the picture of this, we're going to be thinking about the inverted pendulum with angle theta, and we're going to be applying some control torque tau. Okay? This is essentially forcing at the base of this pendulum. And so we're going to essentially cook up a tau that stabilizes this inverted pendulum system. That's what we're doing on the homework. So this is about the theta equals pi solution. So I can write down theta dot equals omega, omega dot equals minus sine theta plus tau. And if I linearize about the unstable fixed point, this theta equals pi, we get something like ddt of theta omega equals 0, 1, 1, 0. But now we have this additional plus 0, 1 times tau. Okay? So we can write down our ODE in this form. And this is exactly like the system we've written up on the left board. So this term is like my vector x dot. This is my matrix A and my vector x. And this is my matrix B. In this case, it just happens to be a column vector. And this is my forcing U. Okay, so we've taken this differential equation for the inverted pendulum with forcing, and I've written it in this simple form in terms of matrices and vectors. Okay, x dot equals matrix A times x plus some other matrix times my input forcing. Okay, and this is really the basis for all of feedback control theory. Okay, so feedback control allows you to change the linear dynamics of a system by adding some external forcing of your choosing. So usually you get to measure some quantities and you get to feed them back and try to stabilize your system. So here our feedback is going to be tau equals minus 2 theta minus 2 omega. And remember, this theta has already been linearized about pi. So this is really my difference from the upright pi position. Okay? And if I plug this in, I find that this whole thing is like 0, 1, 1, 0 times theta omega plus, okay, I get 0 contribution from this torque in the first row equation. but I get minus 2 theta minus 2 omega in the second row equation, because that's what my torque tau is equal to. So this is like a minus 2 times theta omega. This is the effect of my forcing tau. I just cooked up this tau. It took me a little while to figure out that this is a really good tau that actually stabilizes the system. But when we plug this in, we can write this whole equation ddt of theta omega equals the unforced component plus the feedback that I get from this forcing tau. So that's 0, 1, minus 2 times theta omega. Okay, so these are the linear dynamics for the system with control. And you can check that these eigenvalues are actually stable. They're both minus 1. So this is just a simple, motivating example showing that it's really nice to be able to take my system dynamics with external forcing and write it like x dot equals matrix A times x plus matrix B times u. Because then once I decide on my control law, or whatever my forcing I want it to be, I can then plug that in, and I can get a nice, simple, linear system, and I can assess the stability of this closed-loop controlled system. So this class is not about controls. I'm not going to ask you to stabilize systems. I'm not going to ask you to cook up the taus that would stabilize a system, but you should be able to analyze the stability of a system that has control or forcing applied. Okay, so this is kind of what we've done in the homework. Okay, questions about this before moving on? Yeah?
Why is that not minus 1 that day?
I'm sorry?
Why is that not minus 1?
Because I'm linearizing about theta equals pi. So partial of this with respect to theta is minus cos theta, and cos of pi is minus 1, so I get a minus 1. Yeah. Okay, so that was kind of the preamble into our discussion about convolution. And I'm going to try to do this as kind of build up as simply as possible. How many of you have seen the convolution integral for forcing ODEs, for ODEs with forcing? How many of you have never seen this? Okay, great. So we're starting to finally get into some things that most of you haven't seen, and that makes this a little more interesting. So let's think about this system and what the solution x of t looks like. So we really want to know what is the solution to this system for various forcing functions u and for various system dynamics a. And so we're going to start by looking at case 1. And case 1, I'm going to try to make this as simple as possible. We're just going to assume that there is no forcing. So u of t equals 0. And we have some initial condition. Okay? Everyone with me so far? We have this system, but we're going to assume that there is no forcing ever, and we just have an initial condition. So what does the solution of this system look like? What's x of t? I mean, we've solved this a lot, right? So if I get rid of that term entirely, it's just the solution of x dot equals ax for some initial condition. So x of t is equal to e to the matrix A t times x naught, right? And we're going to call this, just like in the last lecture, you could call this the homogeneous solution to this differential equation when there's no forcing, or we're going to call this the initial condition response. This is literally just the response of the system to a pure initial condition with no forcing. Okay. Okay, so for case 2, this one's kind of interesting. We're just going to build up to more and more general systems where eventually we're going to be dealing with an arbitrary input u and an arbitrary initial condition x naught. That's where we're going, but we're just going to build this up in stages. So for case 2, we're going to assume that there is no initial condition, x0 equals 0. So there's no kind of initial condition. And we're going to assume that u of t equals a delta function. And we're going to assume that this matrix B is just in the direction of x naught. So essentially what this means is that this input matrix is just x naught vector. And I'm going to give you a delta function at time 0. So how many of you remember what delta functions are and do? Okay, I'm going to do a little bit of a review of delta functions. Okay, so let's do a little review of delta functions. But this is so we're making this more and more general. So right now we've looked at the case where there's no forcing, but there's an initial condition. Now we're looking at the case where there's no initial condition, but there is forcing. And soon we're going to combine the two, and we're going to say, okay, there's an impulsive forcing and an initial condition. That'll be case 3. Okay, so this function delta t is called the Dirac delta function. Dirac was quite a genius. He essentially gave us the mathematical notation that we use today for most of modern physics. So if you've ever seen like inner products written as like brackets, that's from Dirac. Okay, this is called the bra, and this is the ket. And that's our bracket notation. So Dirac was a really smart guy. And he invented this function delta because all of the functions that had been written down and that people used didn't have enough generality to do the things he wanted to do, to look at point sources and kind of impulsive forcing of systems. So the idea of this delta function is essentially, in time, we're going to try to get unit energy into an infinitesimal amount of time. Okay, it's kind of like we're going to hit our system with a hammer. So in a very, very, very short amount of time, we're going to impart a finite amount of energy or momentum into the system. And so the way we can think about this is that in some amount of time, I might impart energy, at some rate. And if I make that time smaller and smaller, and I double the amount of energy imparted, and I make it smaller and smaller still, the limit, as I make these rectangles infinitely thinner and infinitely taller, is a delta function. So think of this rectangle has height, h, and width, 1 over h. So its area is equal to 1. Now, if I take the limit as h goes to infinity, every intermediate rectangle also has area 1, but they're getting thinner and thinner, and they're getting taller and taller. So the delta function is this kind of mathematical abstraction of the limit as I make these rectangles thinner and thinner and taller and taller. And it has this nice property that if I integrate my delta function in time, the area under this curve is exactly equal to 1 by construction. We made this thing to be a rectangle with unit area, and we took the limit. So this absolutely equals 1. And in fact, if I take the integral from minus epsilon to epsilon, some really small number, like minus 0.01 to 0.01, that also equals 1 for any positive epsilon. Any little number you can name, if I take the integral from negative that number to positive that number, I'll capture this unit area increase because of this delta function. Okay, so this is, you can think of this as an impulse. We're impulsively adding something to our integral. Okay, questions about the delta function? Okay, it's just a special function that we've cooked up that has this property. It always adds up to 1, and it's infinitesimally thin in time. It's instantaneous. Okay. You can also do something where you can delay this in time. So if I have t0 and let's say t5, I can have a delta function at t equals 5. It's just delta t minus 5. Okay, so this is just shifting time by 5 to the right. So at exactly t equals 5, this thing looks like a delta function. And it integrates to area 1 exactly at time equals 5. So these are some of the things I can do with a delta function. Okay, now I'm going to do this example that's going to illustrate case 2. Maybe for case 2, I'll actually make this an impulsive delta function at t equals 5. This is going to make a little more sense. Okay, so my initial condition is 0. My input function is an impulse at time 5. Okay. And so the way I'm going to write this is as follows. I can always take this equation, and I can multiply both sides by dt and integrate. It's not really that useful for computing things, but mathematically I can write that as the solution. I can say x of t is equal to x naught plus the integral from 0 to t of a x of tau plus b u of tau d tau. This isn't really that useful for actually computing what x is, but this is certainly a true statement. This has to be true if this differential equation is satisfied. So any solution x of t will definitely satisfy this integral equation. I literally just multiplied both sides by dt and integrated, and my constant of integration is my initial condition x naught. Okay, not too bad. So what we're going to do is we're going to plot x and u in time, and we're going to see what this impulsive input to u does to our solution x. Okay, so time, this one is going to be u and x. Okay, so our u function is 0, 0, 0, 0, and then at time 5 it's a delta, and then it's 0 forever after. So u looks like a delta at time 5, so this is 0. Okay. It integrates up to 1. And so my x, remember x naught is 0. And so x of t, I'm adding up a times 0, a times 0, a times 0, a times 0 for all time less than 5. This is 0. And bu is also 0 for time less than 5, right? U and x are both 0 up to time 5. So x starts at 0 and stays at 0 until time 5. But at exactly time 5, this delta function integrates up to 1. So at exactly time 5, my x gains an amount equal to b. B times the integral of delta equals b. So we go up to b. And now this is like our initial condition. And our solution just decays as e to the a t minus 5 times the initial condition b. So I'm going to go over this one more time, because this can be confusing the first time you see it. Okay, so what do we have here? We have a system with an initial condition equal to 0. And our forcing is going to remain silent until exactly t equals 5. We're going to give it an impulsive input. and then it's going to remain 0 forever after. So our solution x, if it starts at 0, then x dot equals 0 plus 0. So x dot's not changing until time equals 5. At which point, at time equals 5, we get this delta function in u, which integrates to 1. And since it's got this coefficient of b, it integrates to b times 1. So our solution x at time 5 jumps to an initial condition of b. And then since I turn my control off at that point, this is just like an initial condition response that started at time 5. So I get my natural dynamics e to the at times my initial condition, but now my t is shifted 5 units to the right. It's delayed by 5 units. Okay, questions about this? Does the cartoon make sense? Okay, do the numbers in the cartoon make sense? Does it make sense why we have an a times t minus 5?
Why is it minus 5 not?
So it's minus 5 because let's say I'm at time 6. So if I just imagine that my system started at an initial condition of b, then time 6 here should really look like e to the a times time 1, because it's been 1 unit since that initial condition. So t minus 5 is kind of my new time since this impulse. Okay? Yeah?
Why is x of t 0 equals 5?
I made it, so I gave it an initial condition of x equals 0. So if I had no forcing at all, let's just forget that bu ever existed. Let's say I have x dot equals a times x. This is the solution. But if my initial condition is 0, then x of t is 0 for all time. Okay, so x of t, you can also see it here, right? A times x of tau is 0 until something happens in my input. And so I'm adding up 0 to my initial condition, and it doesn't go anywhere. X stays 0 until there's an input u. Yeah.
I guess I'm a little confused because this is the case where the initial condition is 0 and then there's force, right?
Yes.
So what is the initial condition that you're talking about, which is B?
Okay. So the real initial condition of the system is 0. X at time 0 is 0. The system has no initial state. But then when time 5 rolls around, my system gets this impulse in u, and it jumps my state x. So x at time 5 plus some little instant after time 5 equals b. And now for all time after, this looks like an initial condition of b. So it's kind of like a pseudo initial condition. The real initial condition is 0, but because of this impulse at time 5, our system looks like it has an initial condition of b starting at time 5. And that solution would be, x of t equals e to the a, and my new time is t minus 5 times my initial condition b. And if I made b equal to some vector x naught, then every time you see a b, you would just swap out an x naught. B can be anything.
Why is it exponential? Second part.
Sorry?
So in the graph, why in the second part it's exponential function?
This is a cartoon. So usually e to the at looks like an exponential. I hope it's a decaying exponential. This could be a growing exponential, or it could be an oscillation. But it's going to be whatever e to the at does, starting at time 5 with an initial condition of, whatever my b was. We shifted the solution. Yeah, and that impulse gave us kind of this pseudo initial condition. I think of these as directions. I think of x is a vector in a vector space. It has a direction. And so the initial condition has a direction. X naught is a vector that points in some direction. And B could also be a vector that points in another direction, and we're giving this thing an initial condition in that B direction. Okay, it's kind of the geometric view. Okay, so now we're ready to do something pretty neat. We're ready to add the effects of initial conditions and forcing, right? So remember that for linear systems, if I have two solutions that satisfy my equation, then the sum of the solutions also satisfies my equation. So I can add solutions, and they're still solutions. So that's going to be kind of the whole basis of convolution. Convolution is just a convoluted way of saying linear superposition of a lot of solutions. Okay, I've seen some terrible pictures of convolution drawn that are super confusing, and it's really, really simple. Okay, so case 3 is kind of like a baby convolution. Okay, so for case 3, we're going to basically just add these two. We're going to say, okay, u is still a delta function at t minus 5. And I'm just going to let my input b be whatever it is. I'm not going to specify this matrix B. And I have some initial condition. So now I have an initial condition, and I have some forcing, some impulsive forcing at time 5. So if we have a linear system, we can just take the effect of initial conditions and the effect of an impulse at 5 and just add the solutions together. This is kind of magical, but it totally works. It's actually not magic at all. It's just because our system is really simple and linear. It's x dot equals a times x. Okay, so we have our initial condition response. Let's see. I'm going to try to draw this nicely. Okay. Okay, so for the initial condition, if we acted like there was no forcing, then the initial condition would start at x naught at time 0, and it would do whatever my natural dynamics A are, which I'm going to draw as an exponential decay, but A could be whatever. Now, if I forgot that I had an initial condition, and I thought I only had this impulsive forcing at time 5, then that solution is going to look like it's going to be 0 up until time 5, and then it's going to jump to B, and it's going to do whatever my exponential decay is, whatever my A dynamics are at time 5 are going to kick in for this impulse. So this is the homogeneous solution, right, to no forcing, just the initial condition response. And this is the, you can think of it as the particular solution to the impulse. And to figure out what the true solution is with both of these effects, it's as simple as just adding them both together. Pretty awesome. So let's just add these. This one's a little harder to draw, but not much. Okay, so our solution, at time 0, we have some initial condition, x naught. And until time 5, my initial condition is just decaying due to the e to the at dynamics. So it's just decaying, 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 until at time 5, I get an impulse in u, and it jumps me up another b. And then after that, I continue to decay and decay and decay and decay and decay forever. That's it. This is the full solution. So it's simple addition. It's not that simple. It's but it is just addition. Okay, questions about this part? Anyone? Okay, we're also going to start seeing this in MATLAB in a little bit. We're going to start doing some simulations with generic forcing in MATLAB. But before we do that, I want to write down the full convolution integral for the most generic u. So at this point, we now are able to combine initial conditions with a single impulse in u. And the next step is actually pretty straightforward. What we're going to do is essentially solve this system for an arbitrary function u. You can just like email me some vector u in time, and I can run this through my simulation. And I'm going to assume that that u is a train of very weak impulses. Okay? So the general system, we use convolution. Okay? This one's a little hard to draw because it takes a lot of vertical space, but I'll do my best. So here we're going to see the function u of time, and maybe it looks like something like that. So now this u is not simple. It's not just an impulse at time 5 or time 0. It's this arbitrary function. Okay? But if I think about it, I could say that really this looks a lot like a bunch of very weak impulses being added together. And the reason I say weak is because this u is only changing infinitesimally in time. It's smooth, right? So every little teeny dt, it maybe goes up or down a little teeny du. And that amount that it goes up or down looks like an impulse. So this is a train of weak impulses. And each of them has a strength given by u at time t times dt. And remember, dt is we can take the limit as dt gets infinitesimally small. So I have this continuum of infinitely small, weak impulses that are contributing to this full u function. I have a train of weak impulses. Each of them has a strength u of t times dt. So these are like little delta functions. Delta of t with a strength u of t dt. Okay? Remember, if these didn't have this infinitesimal here, then these would go up to infinity, and when I integrated them, I'd have a discontinuity in my solution, which we know is not going to happen. Okay, so now I'm going to draw the solution x for the initial condition and with the effect of all of these trains of impulsive forcing. Let's see. Okay. So first things first, I'm just going to draw the initial condition response, x naught. So the initial condition response for some initial condition is just, this decay or growth or whatever it does, but it's just some signal that starts at 0 and decays from x naught forever. Yeah? This is just delta of t. It's a Dirac delta function with a strength, with a magnitude of u of t dt. Okay? Good. It's actually got a magnitude of, let me write this slightly better. It's really b u of t delta of t dt. It's got a strength of b u of t times this infinitesimal. Okay. I forgot this b in my notes, but it shouldn't be a big deal. Okay. So there's this initial condition response. But then I also have the response due to all of these little impulses, this whole continuous train of impulses. And so this is a little impulse of size, let's call this T1, T2, T3, ... just to keep track of all these different impulses. So I have this little impulse of strength B u of T1 dt. And that little infinitesimal impulse in U gives me a tiny little transient response starting at T1. Okay, so I had my initial condition at time 0, it just decays. And then at T1, I get this little infinitesimal impulse in U that gives me a response. At T2, I get another little infinitesimal response. This one looks a little bit bigger. And at T3 and T4 and T5 and so on for all of time. So plus, plus, dot, dot, dot forever. And so I can write this as, I'm just starting a cartoon. This train of impulses is a cartoon. But what I can do is I can make these infinitesimally small. I can make dt go to 0. And I can write this as an integral. And so the integral is extremely powerful. We have x at time t is equal to e to the at times x naught, my initial condition, plus this effect of impulsive forcing, plus an integral from 0 to t of e to the a t minus tau times b u tau d tau. Okay, let's think about this for a minute. So every one of these little infinitesimal impulses in U excites a little teeny tiny infinitesimal exponential decay that's shifted in time by the amount that it took that delta to turn on. Here that's tau. So at time tau, I have a little delta, and it excites a response e to the a t minus tau times whatever that initial condition was. Remember, this is literally e to the a t minus t1 b u of t1. This is what we derived from, case 2 and case 3 over there, is that if I had this little impulse at time 1, I would get e to the a, now my time is shifted t minus t1, right? This decay starts at t1, times whatever the strength of that impulse was, which is b u t1 dt. And here we have e to the a t minus t2 b u at t2. So my forcing u at time 2 times dt, and so on and so forth. And I'm literally just going to add or integrate all of those up, and I get this exact expression here. This is the convolution integral. And notice that, so we can write this as, we can call this a convolution integral. This is really e to the at convolved with b u of t. That's what this part equals. So this is the definition of a convolution integral. So this symbol star means this type of integral, where one of the terms is shifted by tau. Okay, so what does this mean? This means that for any linear system at all, for any A matrix and B matrix that you can name, if you tell me x naught and whatever your forcing u is as a function of time, I can compute the solution x at any time by adding up the initial condition response and this kind of time-shifted, integrated train of impulse responses from my input. So every little u is kind of like contributing to my state x, but that's dying out. And so we have to add those time-shifted exponential decays for each of those little impulses in u. Okay, questions? You can try this on an example. I would recommend it, because this is a little bit abstract, but you can do something like, Maybe this will be a homework. I haven't decided. So maybe you have something like x dot equals 5 minus 5x. Let's make it a little simpler. X dot equals minus 2x plus u. And x naught equals 10. And u equals sine t. Yeah.
In the simple convolution, written e to the power 80 convolved with du.
I'm sorry, what?
In what you've written in blue underneath.
Yeah.
But is there supposed to be a tau somewhere? How do we understand how much we shift the?
So this integral is with respect to tau. And so this tau actually disappears from this integral once you integrate. Once you're done integrating this, you're just left with function of t. Yeah, so tau is kind of this thing that's shifting, but you're going to add all those up, and you're going to get x at t equals the sum of all of these things. X at another t is the sum of all of these things at each of those times. So this is a good example to try this out. You can really try this out. This isn't very difficult. You can say, I think we can solve it right now. This is e to the minus 2t times 10 plus integral 0 to t of e to the minus 2 t minus tau sine of tau d tau. And I think you can plug this into Mathematica and integrate e to the something times sine of something. And you'll get some function out, and you can plot it and see if it really makes sense in MATLAB. Okay? Okay, now I want to actually show you some MATLAB code, because this is pretty esoteric. It's not really esoteric, but you only can see the real use of doing this when we have computers solving it for us. Okay? So I probably wouldn't ask any questions about a generic system like this with matrices and something nasty on like a qualifying exam. But I do want you to know about this idea of convolution. It's like I might ask you questions based on this expression and this cartoon. Like I want you to at least have the cartoon understanding of convolution. Okay, so I have about 10 minutes left. I'll just do one last thing and go to MATLAB. So next week, we're going to switch gears entirely to numerical stuff. For at least 1 week, we're going to talk about numerical solutions to really nasty ODEs, which will be a lot of fun, because you can solve way, way harder systems than what we're looking at now. Okay, so in MATLAB, we typically will write down our system like x dot equals matrix A times x plus matrix B times u. But then we'll also have an output equation, which is y equals cx plus du. And the way we think about this, u are the inputs. These are the things you get to force or change or control. And y are the outputs. These are the things you get to measure or sense or detect. Okay, so in a system, u's are the things that you get to force your system with. And y's are kind of the readouts of your state. And x is your internal state. So for our system, we actually want to measure everything. When we do this in MATLAB, we're going to want to measure all of the x's. So we're going to have, I'm going to do this example, theta double dot equals minus sine theta plus tau. And we're going to do this on the pendulum down solution. So we're going to linearize about theta equals 0. And we're going to have d dt of theta omega equals 0, 1, minus 1, 0. So now we have the negative 1. Plus 0, 1 tau. And our output equation is just y equals x. Okay? So this is A. This is B. C is going to equal the identity. And D is going to equal 0. Okay, and what this means is we're going to be able to test out our convolution integral. We're going to be able to give forcing functions tau and simulate what this system does in response, and we're going to measure both theta and omega. So the outputs are going to be theta and omega, because C is the identity. I'm going to code this up in MATLAB. This should be clear once we code it up. Okay. Okay, so I'm going to clear all, close all CLC. And I'm going to define my A matrix as 0, 1, negative 1. I'm going to add a teeny bit of damping, if that's okay with everyone. Okay? B is a column vector 0, 1. C is the identity, a 2 by 2 identity. And D is just 0, 0. I'm going to call this test sim. Okay, so in MATLAB, there's a super, super simple command called SS, and it turns these 4 matrices into a state space system, something I can simulate. So my system equals SS of A, B, C, and D. I save this and I run it, and it takes a little while. But now I have my A matrix, B matrix, C, and D matrices in memory. And I have this sys object. And if I type sys, it tells me I have a continuous state space model, and these are my A matrices, A, B, C, D, and so on. So now I can do something cool, like I can compute the impulse response of my system from time 0 to 100. And it looks like that. So if I gave my U an impulse at time 0, this is the impulse response of my damped pendulum solution. It oscillates and dies, right? Because we're at the bottom, this theta equals 0 solution. And this is both the position theta and the velocity omega. Okay, so that state space representation, x dot equals a times x plus b times u, is really useful. We can plug it into MATLAB and get impulse responses. Impulse responses aren't that great, so I'm going to cook up another signal, which is kind of like a triangle. So my input's going to ramp up and then ramp down. So I'm going to say t equals 0 in increments of 0.01 to 50. And u is going to start by being 0. But then for a little while, u is going to ramp up. You can see what I'm doing after class. I'm just going to write this out. This isn't as bad as it looks. Okay, so this u function I cooked up is just a triangle wave. It starts at 0, it goes up to some value, then it goes back down, and then it stays 0. And I can do something called LSIM. So here, let's just plot t by u. That's my control input. So this tau forcing function starts at 0, then it ramps up to 0.1, then it ramps down and stays at 0. And there's a function called LSIM, linear simulation. So I put in my system, my control input, and the amount of time I want to simulate. And it will simulate my system with that control vector u, that input forcing kind of tau, in time. And this is what it looks like. So if I give my system an input that looks like this very gray triangle, then these blue curves are theta and theta dot for that input forcing. You could literally build this system. You could build a pendulum and have something that can apply torque at the base, and you can give it this signal, and this is what the pendulum is going to do. Okay, MATLAB is using convolution to compute this solution. Like it's being clever, and it's actually computing these integrals in a clever way so that it gets this blue response. Okay, so I want you to play around with this. This is awesome stuff. You can really do powerful things with linear systems, and we're going to build up the numerics to do nonlinear systems in the next week. Okay, happy studying. See you on Monday.